Okay, so back to the proof of that power series expansion. Z minus zeta, right? This is what we had in the integral formula, right? Fz over so you have to remember the picture we drew earlier. So this is Z naught, some point whatever, zeta here and z here, so on. So now you have to bring in Z naught. So pull out right? That's all. So this has modulus less than 1. So this is the picture, right? Mod z minus z naught, zeta minus z naught is less than mod z minus z naught. So you pull out 1 over z minus z naught. So this has modulus is less than 1. So you get this expansion for this, namely right? Of course, if you bring in z inside if you want, so this is going to be so the series being uniformly and absolutely convergent on all compact subsets of the disk where this is less than 1. Of the relevant disk. Local uniform convergence means uniform convergence on compact subsets, on any closed disk, for example. So in particular, on a circle, it's uniformly convergent. So now you can integrate over a circle, a small enough circle. So you have zeta here. So integrate over some circle there. Because of uniform convergence, you can integrate term by term. Circle C around zeta, okay? whatever r inga pottana I didn't use r there, so whatever some radius. Suitable just means that the disk lies inside the domain, that's all. What do you get? On the left hand side, you are going to get integral of this 1 over 2 pi I can multiply 1 over 2 pi I integral. Let's just call this C, okay? C. I mean, after multiplying by f, integrate, right? What do you have there on the right hand side? Is that right? 1 over 2 pi I. I'm just multiplying by 1 by 2 pi I fz and then integrating. Okay? Any mistake? Huh? Right side? F of z, yes. Summation, yes. Now this numerator doesn't involve z, so you can pull it out. One by 2 pi I. So this is a constant as far as zeta is concerned. There is no zeta here. So call this as an if you want. So this is sigma an zeta minus z naught power n, where an is 1 by 2 pi I fz over okay. So of course the series being convergent, any disk with center z naught and contained in the domain omega. Yeah, there. Oh, maybe there is a conflict with R there. This R is different from that R, so something. But from power series expansion, we know that ANs are given by this, right? So this AN, same as that AN. So this is equal to 1 over 2 pi I, whatever, have integral C fz over z minus z naught over n plus 1. What is that? This is these are the coefficients that we get from our actual expansion. But we know once you have a power series, these are the coefficients. So this is equal to this. That's all. So incidentally, you also have now Cauchy's formula for the derivatives. Right? The nth derivative is given by n factorial times this. N equal to 0 gives you the Cauchy integral formula. And you also see therefore that Fn z naught is equal to n factorial over 2 pi I f of z, z minus z naught. So these are the Cauchy formulas for the derivatives. Cauchy's integral formula if you want.
Maximum of mod m circle.
This is some r power something or whatever, and then dz will go off. So you will get the length of this. So 2 pi r or whatever it is. So the 2 pi will cancel off. I will go, of course, when you take the modulus. So what do you get? So 2 pi goes off. R will be there, right? From this. N factorial is there. Bro. Why? What do you get? R power? So this itself is R, right? Z is on the circle, so mod Z, Z not R power n plus 1. There is one R that goes away from the length of C. So 1 over R power n. So Cauchy's estimates for the derivatives. So it's a compact set, so no problem. Even if you write supremum, doesn't matter. Same as the maximum. So you have therefore estimates for all the derivatives of the function. So what can you conclude from this? If f is okay, so first let me ask the following thing. If you have an analytic function whose derivative is 0, what do you conclude? An analytic function whose derivative is 0. If f prime is 0 identically on the domain, then what is the conclusion? F is constant. Sure. There is some topology involved there. Suppose your domain, the union of two, say, disjoint disks, and the function is 1 on this and 2 on this. Okay? So what is the derivative? Derivative 0 here as well as here. So on the whole domain, therefore, the derivative is 0. But what about the function? Is it a constant? No, it's 1 here and 2 here. So what is the, so this is of course what a blind statement. The derivative is 0, the function is a constant. But not at the PG level at least. So what is wrong with this example? What was the problem with this example? The domain is not connected. Okay. We have two disjoint disks, not connected. So the correct statement would be if F is analytic on a connected domain and F prime is 0, then F is a constant on that domain. Or slightly more generally if you want, if the derivative is 0 on a domain, on a domain, F prime is 0 on a domain omega, then F is locally constant. Constant on each connected component, if you like, or constant in neighborhood of each point. So that's the correct general statement. But what is the proof for that? Let us look at the correct connected case. The derivative is 0 and the domain is connected. How do you prove that is a constant? So where does this connectedness come in? Proof. First of all, how do you get the function is 0 somewhere in some neighborhood of something at least to start with? Look at the power series expansion, right? The coefficients all involve all the derivatives, right? The nth coefficient is whatever, what was that? N factorial by whatever, so on, right? Fn something, the derivatives, right? If the derivative is 0, then what are you going to get? All the ans are going to be 0 except a0, right? The constant term in the power series. a0 plus a1 z minus z naught plus a2 z minus z naught whole square and so on. Okay, so all the coefficients are going to vanish at z naught if, I mean in the neighborhood of z naught actually, the power series expansion is valid in a disk around z naught. So in the whole of that disk, except a0, all the other ans are 0, which means the function is a constant in that neighborhood. But this you can do for any point in the domain. You can expand around any point in the domain. Okay? Take z0 to be any arbitrary point in the domain. You have a power series expansion around that, and the same thing shows that. So in that neighborhood, the function is a constant. So in a neighborhood of each point, the function is a constant, right? That means f is a locally constant function. If the domain is connected, what happens? So look at the set of all points where the derivatives are 0 or the function is a constant, or whatever. Both mean the same, right? So what can you say about this set? Set of all points z0, let's say, where f and z0 is 0 or f prime z0 is 0, whatever. So what are you going to get? So in the whole of that neighborhood, all the ans are 0, right? So the function is a, so whatever you assume for z naught also hold for all points in that neighborhood, that all the derivatives are 0, right? Or the function is a constant. So what does this show? The set of all points where this conclusion holds, around each point in that set you have a neighborhood which is contained in that set, right? Which means that set is open. Set of all points where all the derivatives are 0 is an open set. But really it is a closed set because set of points where a continuous function vanishes is a closed set, right? The 0 set of a continuous function, what is this? This is f inverse singleton 0, right? If f is continuous, this set is closed. Singleton 0 is closed, so the pullback is closed. So the 0 set of a continuous function is always closed. So all our functions are more than continuous, right? The derivatives. So the 0 set is always closed. But what we get from the power series expansion is that it is also open. Okay? So if you have a set which is both open and closed in a connected space, so what do you conclude? It is either the whole thing or the empty set, right? But it is not the empty set in this case because at least at some point you are assuming that the derivative is 0. So the conclusion is that the function is a constant on the whole domain. The domain is connected. So in general, the vanishing of all the derivatives gives you that the function is locally constant. When the domain is connected, this reduces to the conclusion that the function is a constant on that domain. Okay? Constant, locally constant is equivalent to constant on each connected component. So if the domain itself is connected, then it is going to be a constant on the whole domain. Okay? Clear? So why don't you write down? You look at this set of all points where whatever E. So this is the intersection of zero set of the nth derivative. The nth derivative is a continuous function. So each of these is closed, so the intersection is closed. On the other hand, E is open. Why is E open? If Z0 is in E, consider the power series of F around Z0. Around Z0 means in a neighborhood of Z0. Okay, in a disk around Z0. Fz equal to an Z minus Z0 for n. So we know what an is. So what is the an in terms of the derivatives? Fn Z0 by n factorial. Is it? Whatever, you write the correct value there. So, but by assumption, Z0 is in E, so everything is 0 except the constant term in the power series. So you just get A0 there, or Fz0 by n factorial. Fz0, n factorial is 1 anyway, equal to A0, of course. The constant. So in that whole neighborhood, Fz is a constant, right? So the derivative is 0. Of course, constant functions always have derivative 0. Whether the domain is connected or not, doesn't matter. Of course, here everything is connected. You have a disk, but you don't need any topological intervention there. So a neighborhood of Z0, therefore, is contained in E. F prime is 0 in that neighborhood. Okay. And neighborhood, whatever, D of Z0 and D is contained in. All the derivatives are 0, in fact, not just F. All Fn's are 0. So E is also open. Nth derivative is 0 for all points in that neighborhood. அங்கே ஒரு பேர் கொடுத்துருக்கலாம், but okay. The function is a constant in that neighborhood, so all the derivatives are 0 at that neighborhood. So the set is therefore both open and closed. So if the set is not empty, then it's the whole thing, therefore. So since omega is connected, okay, of course, they pointed out if omega is not connected, we conclude that F is locally constant. So what do you mean by locally constant? Constant in a neighborhood of each point. So that is equivalent to saying that it is a constant in each connected component of omega. So recall the Cauchy estimates there. on something r power n, right? The radius power n, where you have the power series expansion. R is the radius of the disk, where you have power series expansion. So in particular, for example, for the derivative, the first derivative, we have this. Suppose f is bounded, which means that you can replace, so this is a maximum not on the whole domain, it is not finite, but on that circle that on which you are integrating. But if the function itself is bounded by some constant m, let's say, so you can replace this by m. Oh, f prime in factorial. So m by r, where m is independent of z naught, right? For all not if f is bounded. For all points in the domain, okay? But suppose in addition that f is, your domain is the whole plane. That means you can expand a power series around any point. Okay, so what do you get therefore? The power series expansion is valid the whole plane around any point. So you can let R to tend to infinity, right? So this is fixed, this is a constant. So if R can go to infinity, if R can be taken to be arbitrarily large, then this is going to be arbitrarily small, which means f prime is going to be 0. Which means that f is a constant. Because your domain is the whole plane now, this is connected. Okay? So what is that we have now? If you have a function which is analytic the whole plane and is bounded, then it's a constant. What is this? Huh? What is this known as? So what does this say? A bounded entire function is a constant. There is a function which is analytic in the whole complex plane and which is also bounded. Must be a constant. There are no non-constant functions, entire functions which are bounded. So what is the proof? This is the proof. Just an immediate consequence of Cauchy estimate, right? F prime z naught is less than or equal to, suppose f z is bounded by m, then this is m by r. What is r? R you can take to be anything, right? Power series converges everywhere in the plane. So you can let R tend to infinity. double L E is pronounced something like yeah. This, how do you read this? Liu. So you read something of this kind. ILLE is pronounced like ya, E, Liu V. V, this I is also dirgham. So for example, what about the function sin z and cos z, the complex plane? So as soon as you say a sine function, you say it's bounded, right? Bounded by 1. But what does, for example, this say? Lewis theorem say. Sin z, is an entire function, right? It's not a constant. So sin z and cos z are not bounded. Of course, this you can see using Euler's formula also. What is sin z e power something minus e power something by something. Okay. So if you look at e power z, is e power x into cos x plus I sin x, I sin cos y plus I sin y. So cosine and sine are bounded, but e power x is not bounded, right? So anyway, so that's a what? Warning, let's say. Don't immediately say that the sine and the cosine functions are bounded. So as far as the real domain goes, it's fine. For right, real x, sin x and cos x are bounded, but not for complex values. Basically, because say, for example, e power iz, when you say e power ix, its modulus is 1, but e power iz, modulus is not 1, right? E power iz is unbounded, and therefore these are unbounded. Maybe I can make some general noises at this stage. Much stronger result is true than Lewis theorem. What are the values that an entire function takes? What can I say about the set of values of an entire function? It's not a bounded set unless the function is a constant. But can you say anything more than that? Can it be any unbounded set? Are there functions, entire functions, which takes all complex values? All complex values?
With one possible exception.
What? Which takes that? Now, which function takes all complex values except one? You have an example of a complex value, an entire function which takes all complex values except one value. And what is that value? A very familiar function. What are the entire functions that you know about? Familiar entire functions. Polynomials. Other than polynomials, the most common examples are exponential function, sine, cosine, and so on. What about polynomials? Take a non-constant polynomial. What values does a non-constant polynomial take? Okay, first give me one function, one entire function which takes all complex values. Identity function, z, right? What about z square? Does it take all complex values? So can you rephrase the question? So what is the meaning of saying that a function fz takes a value alpha? What does it mean? This equation has a solution. That means there is some z for which f of z equal to alpha. Right? F takes a value alpha means there is some value of z for which f of z equal to alpha. So look at z square now. Take any alpha. So do you have z for which z square is alpha? First yes or no, and then we can come to the value. So you can rephrase this by asking whether every complex number has a square root. Right? That's what this means. Right? Does every complex number have a square root? Yes or no? One square root. I mean, right now we are not worried about how many square roots are there and so on. Does this have at least one square root? Yes. So if, for example, if you write in terms of polar coordinates, forget z equal to 0, alpha equal to 0. If alpha is 0, z is 0. So write in terms of polar coordinates, and then r e power I theta. So square root of r e power I theta by 2 is going to be a square root. So what is the conclusion? So z square also takes all complex values. So now tell me the general statement of this kind. Huh? Every polynomial, non-constant polynomial, takes all complex values because every non-constant polynomial has a root. We are going to prove that right now, but that's something that you know already, right? So polynomial, non-constant polynomials take all complex values. So these are examples of entire functions which take all complex values. Are there examples of entire functions which do not take all complex values? E to the z, exponential function. What value does it not take? E power z is never 0, right? E power z and e power minus z is 1. So the left hand side can be never 0. Are there any other values that the exponential function does not take? So this is an exercise. The exponential function takes all value, e power z takes all complex values except 0. Okay? So we have entire functions which takes all complex values, namely non-constant polynomials. We have entire functions for which there is one exception, right? E power z does not take the value 0. So can you think of an entire function for which there are two exceptions? An entire function which does not take two different complex values a and b, let's say. You cannot possibly come out with an example because there is no such function. So in other words, so what is the statement? A non-constant entire function cannot omit more than one value. Or in other rephrasing, an entire function which omits two values is a constant. Okay? Now look at the Lewis theorem that we have proved. What does it say? Is bounded. So which means the range of the function lies in the disk. Mod z is less than or equal to m. So for every z, f of z lies in this disk. So every point outside the disk is not a value of the function. So it omits a huge lot of values, right? But whereas what I stated a moment ago, and if an entire function omits two values, it must be a constant. You see that that's a much, much, much stronger statement than Liouville's theorem. Okay? So this is known as the little Picard theorem. An entire function which omits two complex values. Is a constant. We will not be proving this, I guess. So, but just to put Liouville's theorem in context, right? So, a rather weak result in some way compared to the Picard theorem. But why is it called little Picard? When there is something little, there must be something big. There is something called the big Picard theorem or the great Picard theorem. I will not go into that now. That's something to do with essential singularities. When we come to that, maybe I will mention that. You have the Parthasarathy theorem, if you remember. So that the big Picard is a far-reaching generalization of the Parthasarathy theorem. Of course, the Picard is the same Picard. It's not that there was a little Picard and there was a great Picard. But the theorem is little and the theorem is big. Of course, even the little Picard theorem is not all that easy to prove. But actually, you can prove it rather easily if you use some what is called Alphonse lemma, which is, by the way, a geometric statement. It connects curvature with analytic functions. We have heard of Schwarz lemma, right? So it's a generalization of Schwarz lemma, sometimes called Alphonse Schwarz lemma. Schwarz lemma is actually a geometric statement again. So anyway, so if you use Alphonse Schwarz lemma, this follows rather easily. Okay, so anyway, the point here is that a result much stronger than Liouville's theorem is valid. Okay. Of course, once you have Liouville's theorem, the usual thing is to deduce the fundamental theorem of algebra. All of you know what it is, and also know probably how to prove this. This theorem has hundreds of different proofs, the fundamental theorem of algebra. The one that is usually given in courses is using complex analysis. You can either use Liouville's theorem, or you can use Cauchy's estimate, or you can use what is called Rouché's theorem, and so on and so forth. There are many ways of proving this using complex analysis. So let's just look at one, maybe two. So what does this say? So probably the name, the Fermat theorem of algebra is from Gauss. So he called it that Grundlacher-Sartz, which means of theory of algebraic equations or something. So Grundlacher-Sartz means theorem, Grundlacher means fundamental. So probably the name is derived from what Gauss used for referring to this theorem. Must have all seen how to derive this using Lewis theorem, right? Basically, what is the, so what does it say? A non-constant polynomial with complex coefficients has a 0 in the complex plane. So if you proceed by reductio ad absurdum, by contradiction, so assume that a polynomial pz never vanishes in the complex plane. So which means you can look at 1 over pz, which is an entire function now. If pz is nowhere 0, 1 over pz is an entire function, right? But if p is non-constant, what happens to the polynomial as mod z increases? If you have a polynomial of degree n, right, basically as mod z tends to infinity, it behaves like z to the n, right? So in other words, it will tend to infinity as mod z tends to infinity. Okay? So what happens now? 1 over mod pz tends to 0 as mod z tends to infinity. If you assume that pz has no zeros in the complex plane, the conclusion is that 1 over mod pz goes to infinity as mod z goes to infinity. 1 over mod pz goes to 0 as mod z goes to infinity. Pz goes to infinity, so 1 over pz goes to 0. So if your function, the continuous function of course, if your function goes to 0 at infinity, then it is bounded. Why? If you have a function which is continuous, let's say, and goes to 0 at infinity, then the function must be bounded. So goes to 0 at infinity means what? For large mod z, this is small, less than 1, for example, for sufficiently large n. That is for mod z, say bigger than some capital R or something, okay? For any epsilon, you can get an R, so take some constant here. So there is an R such that the function is going to 0 at infinity. Then there is an R such that for mod z greater than R, this is less than 1. Right? So this means outside a disk of radius R, the function is bounded by 1. Right? But what happens inside the disk? Mod z less than or equal to R. It's a compact set, right? A closed disk. It's a compact set. So if you have a continuous function on a compact set, it is bounded. So on mod z less than or equal to R, f is bounded by something, m, whatever. So fz is therefore bounded by a maximum of m and 1 everywhere. Okay? So that means in our context, therefore, it means that 1 over pz is an entire function and is bounded. And then invoke Lewis theorem. Okay? So conclusion is that pz is a constant. 1 over pz is a constant, which means pz is a constant. So we started with the assumption that pz is not a constant. We conclude that pz is a constant. So clash. That's the proof. This is proof that you normally see, I suppose, in your courses. But what about Cauchy's estimate? So I'm not going to write down the proof that we just now recited, so to say. You have to write down the proof, okay? I haven't written the statement either, but all of you know what the statement is. Any non-constant complex polynomial has a complex root. Can you use Cauchy's estimate also to prove this fundamental theorem of algebra? I mean, if you look at the way we proved Lewis theorem, we used Cauchy's estimates, right? So instead of using Lewis theorem which used Cauchy's estimate, we can as well directly use Cauchy's estimate. So how do you get that proof? How do you write that proof? Start with the same kind of things. Suppose pz is a non-constant polynomial and it has no zeros in the complex plane. It's bounded as before, 1 over pz is bounded. I mean, just repeat the proof of Lewis theorem, right? If 1 over pz is bounded, suppose taking f is equal to 1 over pz, f is an entire function and satisfies this for all points. So you can let r to go to infinity and conclude that f prime is 0, right? So f prime is 0 everywhere in the plane, so f is a constant. So you conclude that, I mean, essentially the same proof as Lewis theorem, now repeated for 1 by pz, assuming that pz has no roots. So you conclude as before that 1 over pz is a constant, which means pz is a constant. Okay? So essentially the same proof, except that we repeat Lewis theorem's proof rather than quoting Lewis theorem. Okay, so there is something called Rouché's theorem, which also you can use to prove this. So please write down the statement. Oh. What is the statement? Every non-constant polynomial with complex coefficients, or complex polynomial if you want, has a 0 or has a root in the complex plane. Because as I said, fundamental theorem of algebra can be proved in so many ways. You can use topology, for example, to prove that. What is in topology also you can do different things. At least something that you will look at, what is called homotopy. It can be used to prove the fundamental theorem of algebra.